Look up, that's all it takes to begin, to tilt your head toward the heavens and feel the weight of something far greater than yourself. The night sky isn't just a scattering of lights, it's a living story, a cosmic tapestry woven from billions of years of starlight, gravity, and mystery. Every twinkle you see is a sun, some long dead, their light still traveling across the void to reach us. Others are being born right now, in nurseries of gas and dust so vast they defy comprehension. This is where science and poetry collide, where the cold, hard facts of astrophysics melt into something almost spiritual. Today, we're not just exploring the universe, we're stepping into its rhythm, its heartbeat, to understand how the poetry of the stars is written in the language of equations. Think about the last time you stood under a truly dark sky, far from city lights. Remember that moment when your breath caught in your throat, when the Milky Way stretched overhead like a river of diamonds. That feeling, the awe, the wonder isn't just emotion. It's the universe speaking to you, inviting you to listen. Because behind every constellation, every swirling galaxy, there's a story science can tell us. Take the Orion Nebula, for example, a birthplace of stars where gravity sculpts clouds of gas into new suns and planets form in the shadows. It's a scientific fact, yes, but it's also a cosmic ballet, a dance of creation that's been unfolding for eons. This video is an invitation to see the cosmos differently, not as a collection of distant objects, but as a living, breathing masterpiece. We'll trace the life cycles of stars, from their fiery births to their explosive deaths, and ponder the invisible threads of dark matter holding galaxies together. We'll marvel at how supernovae scatter the very elements that make up our bodies across space, connecting us to the stars in the most literal way possible. And through it all, we'll celebrate the artists and scientists who have helped us decode the universe's secrets, turning data into dreams. So let's begin this journey together, where every fact is a brushstroke and the night sky is the canvas. The cosmos is waiting, and its story is more breathtaking than you've ever imagined. Deep in the swirling heart of a stellar nursery, where temperatures plunge to near absolute zero and clouds of gas stretch light years across, something miraculous happens. Gravity, patient and relentless, begins to pull. Dust particles drift closer, hydrogen atoms whisper together, and slowly, over hundreds of thousands of years, a knot forms. This is how a star begins, not with a bang, but with a whisper, a delicate gathering of scattered stardust into something dense enough to ignite. Picture the Orion Nebula, that glowing jewel in Orion's sword. To the naked eye, it's a faint smudge, but through the lens of telescopes like Hubble or James Webb, it transforms into a storm of color and motion. Towering pillars of gas, sculpted by stellar winds, cradle fledgling stars in their folds. These infant suns, still wrapped in veils of dust, flicker to life as nuclear fusion sparks in their cores. It's a violent process, really gravity-crushing atoms until they fuse, releasing energy that pushes back against collapse. A star is born in this perfect tension, a balance between inward pull and outward fire. But here's the wonder. The same hydrogen atoms drifting in those clouds have existed since the dawn of the universe. They've been part of ancient stars, supernova explosions, perhaps even other worlds. Now they're becoming part of something new. Science tells us this with equations and spectra, but poets have always sensed it too. The Romantics called stars the forgotten language of the divine, while modern artists paint nebulae as cosmic wombs. Both are right. A star's birth is physics in its purest form, yes, but it's also a testament to the universe's endless capacity for reinvention. Consider this: every element heavier than hydrogen in your body, the calcium in your bones, the iron in your blood, was forged in the heart of a star. When we study stellar nurseries, we're not just observing distant events. We're tracing our own lineage. The carbon in your DNA, the oxygen in your lungs, all of it was once stardust, scattered across space by dying stars and gathered anew. That's the real magic of these cosmic cradles. They remind us that creation isn't just happening out there. It's written into every atom of our being. There's a point in space where the rules, the laws of physics as we understand them, simply stop working. A place where gravity becomes so overwhelming that not even light can escape its grip. This is the realm of the black hole, a cosmic phenomenon so bizarre it feels ripped from the pages of a fantasy novel. Yet, these gravitational monsters are very real, born from the ashes of massive stars that have collapsed under their own weight. Einstein's theory of relativity gave us the math to predict their existence, but even he struggled to believe something so strange could actually exist in our universe. Take the event horizon, the black hole's point of no return. Cross this invisible boundary, and there's no coming back. Time itself distorts here, stretching seconds into eternities for an outside observer. And if you were to fall in, the tidal forces would pull you apart in a process gruesomely nicknamed spaghettification. Your body stretched into a thin, noodle-like strand before being crushed into the singularity, a point of infinite density where all known physics breaks down. It's the universe's most extreme demolition derby, where matter isn't just destroyed but rewritten into something beyond our comprehension. But black holes aren't just cosmic shredders. They're also paradoxes, challenging everything we think we know. Stephen Hawking stunned the world when he theorized that black holes aren't entirely black, they slowly leak radiation, evaporating over unimaginable timescales. This discovery bridged quantum mechanics and relativity, two pillars of physics that otherwise refuse to play nice. And then there's the information paradox. If matter swallowed by a black hole is lost forever, it violates a fundamental law of quantum physics. Scientists are still wrestling with this, some suggesting that black holes might encode information on their surfaces like holograms, preserving the universe's deepest secrets in ways we're only beginning to grasp. Artists and storytellers have long been captivated by these enigmas. Jorge Luis Borges envisioned a black hole as a labyrinth of forever, a place where time folds in on itself. Christopher Nolan's Interstellar gave us Gargantua, a spinning black hole rendered with such scientific accuracy that physicists published papers about it. These creative interpretations aren't just flights of fancy, they help us grapple with concepts too vast for equations alone, because at their core, black holes are more than astronomical objects. They're mirrors reflecting the limits of human knowledge and our relentless drive to push beyond them. Perhaps that's the true allure of black holes. They exist where certainty ends and wonder begins, reminding us that the universe still holds mysteries no telescope or equation can fully unravel. They challenge us to rethink reality itself, blending the cold precision of science with the boundless curiosity of the human spirit. And in that tension between what we know and what we dream, we find the magic of cosmic exploration. Imagine a spiderweb glistening with dew at dawn, delicate, nearly invisible, yet strong enough to catch the morning light. Now stretch that web across billions of light years, threading through galaxies like beads on a string. That's dark matter, the unseen architecture of the cosmos, holding everything together without so much as a whisper. We can't see it, we can't touch it, but without it, the universe as we know it would fly apart. Here's the paradox: dark matter outweighs visible matter 5 to 1, yet it refuses to interact with light. Stars, planets, even the dust between them, all of that accounts for less than 5% of the universe's total mass. The rest, a cosmic phantom felt only through its gravity. When astronomers first noticed galaxies spinning faster than they should, their outer stars whipping around as if gripped by invisible hands, they knew something was missing. That something is dark matter, the universe's silent choreographer, keeping galaxies from tearing themselves apart. The hunt for this elusive substance reads like a detective story. Scientists have turned entire mountains into laboratories, shielding sensitive detectors from cosmic rays in hopes of catching a single dark matter particle bumping into an atom. Others collide particles at near light speed in machines like the Large Hadron Collider, searching for clues in the debris. And then there are the cosmic maps, where astronomers trace dark matter's presence by how it bends light around galaxies, a phenomenon called gravitational lensing. It's like tracking a burglar by the footprints they leave in shadows. Yet for all our tools, dark matter remains just out of reach. Some theories suggest it's made of weakly interacting massive particles, while others propose actions, particles so light they're almost imaginary. There's even a chance we've got it all wrong, that dark matter doesn't exist at all, and gravity itself behaves differently on cosmic scales. It's a humbling thought. After centuries of unraveling the universe's secrets, we might still be missing a fundamental piece of the puzzle. Artists and philosophers have long been drawn to this mystery. In folklore, darkness isn't empty, it's alive with unseen forces. Modern poets write of dark matter as the universe's unfinished symphony, notes we haven't learned to hear. And perhaps that's the most beautiful part of this search. Dark matter doesn't just challenge our instruments, it challenges our imagination. It reminds us that reality is more than what meets the eye, that even in the void there's structure, purpose, and a story waiting to be told. So the next time you look up at the night sky, remember, you're seeing only a fraction of the tapestry. The rest is woven from threads we're still learning to trace, a hidden framework turning chaos into cosmos. Dark matter isn't just a scientific enigma, it's an invitation to wonder, to explore, and to embrace the profound truth that the universe always has another secret up its sleeve. What if every decision you've ever made, every path taken or left unexplored exists somewhere, playing out in a universe just beyond our grasp? The multiverse theory isn't just science fiction. It's a serious scientific hypothesis, born from the strange rules of quantum mechanics and the mind-bending math of cosmology. At its core, it suggests that our universe might be one of countless others, each with its own unique laws, histories, and even versions of you. Somewhere out there, a universe exists where dinosaurs never went extinct, where the Roman Empire never fell, or where you chose that other job, that other love, that other life. The idea didn't spring from nowhere. Quantum mechanics, the study of particles at the smallest scales, shows that particles exist in multiple states at once until observed, a phenomenon called superposition. Extend that logic to the cosmos, and you get the many worlds interpretation. Every quantum decision branches reality into new timelines. Meanwhile, cosmic inflation theory suggests our universe might be one bubble in an endless froth of universes, each with different physical constants. Some might have stronger gravity, making stars burn out faster. Others might lack dark matter entirely. The variations are as infinite as the multiverse itself. Scientists are divided. Some, like string theorist Brian Greene, argue the multiverse is a natural consequence of the math we already trust. Others, like Nobel laureate Roger Penrose, dismiss it as untestable speculation science fiction in a lab coat. And yet, the debate itself is thrilling. It forces us to ask, what is science if not the art of imagining possibilities, then testing their limits? The multiverse might be unobservable, but its shadow appears in the cosmic microwave background, the afterglow of the Big Bang, where some researchers claim to see bruises from collisions with other universes. Storytellers, of course, have run wild with the concept. Marvel's Spider-Man Into the Spider-Verse turned the multiverse into a kaleidoscope of heroes, each with their own flair. Philip K. Dick's novels explored how shifting realities could unravel identity itself. Even ancient myths, from Hindu cosmology's endless cycles of creation to indigenous Dreamtime stories, hint at parallel worlds. These aren't just flights of fancy, they're cultural echoes of a question science is now asking in equations. Are we alone in existence, or is reality far stranger than we dared to dream? The multiverse does more than expand our cosmic address. It reshapes how we see ourselves. If infinite versions of us exist, does choice lose meaning? Or does it become more precious, knowing each decision carves out a unique path in the vastness? Maybe the answer lies in between, not in proving the multiverse exists, but in letting it stretch our imaginations. After all, every great discovery began as someone's wild thought. Whether the multiverse is real or not, it reminds us that the universe is bigger, weirder, and more wondrous than we ever imagined. And that's a truth worth exploring. When a massive star dies, it doesn't fade quietly. It explodes with the fury of a billion suns, leaving behind a core so dense it defies logic. This is the birth of a neutron star, a cosmic diamond forged in the heart of a supernova. Picture this, a sphere no larger than a city, yet packing more mass than our entire sun. If you could scoop up a teaspoon of its material, it would weigh as much as a mountain. That's not just heavy, that's the universe bending the rules of physics until they shatter. These stellar remnants spin with dizzying speed, some rotating hundreds of times per second. As they whirl, they become pulsars, lighthouses of the cosmos, shooting beams of radiation across space like a cosmic metronome. The Crab pulsar, for instance, flashes 30 times a second with such precision that astronomers once mistook its signals for artificial evidence of alien intelligence. Instead, it was nature showing off its ability to keep time better than any atomic clock we've ever built. But the real magic happens beneath the surface. Under that crushing gravity, atoms collapse into a sea of neutrons, squeezed so tightly they form exotic materials we can't recreate on Earth. Some theories suggest the cores of neutron stars might contain nuclear pasta, a bizarre state of matter where protons and neutrons align into shapes resembling spaghetti or lasagna sheets. And near the surface, crystalline structures so dense they're essentially cosmic diamonds, glittering in the darkness. Neutron stars aren't just scientific curiosities, they're bridges between disciplines. Physicists study them to test the limits of quantum mechanics and gravity. Artists turn their rhythmic pulses into music, translating the cosmos into sound. Ancient cultures, unaware of the science, wove their steady beats into mythology, calling them the heartbeat of the gods. Even today, their signals guide spacecraft like GPS for the galaxy. Perhaps the most astonishing thing about neutron stars is how they balance violence and elegance. Born from cataclysm, they become beacons of order. Their gravity could shred a planet, yet their pulses are so regular they rival the finest Swiss watches. They're proof that even in the universe's most extreme corners, there's a strange kind of harmony, a reminder that destruction and beauty often share the same celestial stage. For centuries, we wondered if other worlds circled distant stars until one night in 1992, when everything changed. That's when astronomers confirmed the first exoplanet orbiting a pulsar, a discovery that shattered our cosmic solitude. Today, the count stands at over 5,000, and each new world rewrites what we thought possible. Take Kepler 10b, a scorched planet so close to its star that its surface is molten lava, or Gliese 486b, a super-Earth with an atmosphere thick enough to crush metal like paper. Then there's the real showstoppers, Hycean worlds, shrouded in endless oceans beneath hydrogen skies, where life might thrive in ways we've never imagined. The tools of this revolution are nothing short of miraculous. The Kepler Space Telescope, our silent sentinel in the dark, used the transit method, catching the faint dimming of starlight as planets crossed their suns. But the James Webb Telescope, that's where the magic gets deeper. Its infrared eyes can dissect the light filtering through an exoplanet's atmosphere, sniffing out chemical signatures like a cosmic bloodhound. Oxygen, methane, even industrial pollutants, any hint of a fingerprint we'd associate with life. Scientists aren't just hunting for Earth twins anymore. They're chasing possibilities, planets with purple photosynthetic bacteria, silicon-based life forms, or ecosystems built around volcanic vents. Science fiction saw it coming, of course. From the twin suns of Tatooine to the floating mountains of Pandora, storytellers painted these worlds long before telescopes found them. But reality has a way of outdreaming even the boldest fantasies. Consider WASP-17b, a planet so puffed up it's less dense than styrofoam, or TRAPPIST-1's 7 rocky siblings, huddled so close a year their lasts mere days. And then there's K2-18b, a tantalizing mini-Neptune, where the Webb telescope spotted water vapor and potential signs of dimethyl sulfide, a gas produced by marine algae on Earth. Could it be a false alarm? Absolutely, but that's the thrill of the hunt. Every data point is a whisper in the dark, a maybe that keeps us leaning forward. What drives us isn't just curiosity, it's something deeper, older. The same urge that made ancient cultures trace gods in the stars now fuels billion-dollar telescopes. Because finding life, even microbial, would be the ultimate plot twist in humanity's story, proof that we're not the universe's only experiment in consciousness. The search for exoplanets isn't just astronomy, it's archaeology of the future, digging through light years to answer a question carved into cave walls and spaceships alike. In all this vastness, is anyone else home? Until we know, every new world is a mirror reflecting not just what's out there, but why we can't stop looking. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars, so many that Earth should be just one tiny voice in a crowded cosmic conversation. And yet, when we listen, all we hear is silence. This eerie quiet is the heart of the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If life is common, why haven't we found a single whisper of another civilization? The question gnaws at our curiosity like no other, because the answer could rewrite humanity's future or hint at its end. One unsettling possibility is the Great Filter, a hypothetical barrier that prevents life from reaching interstellar stages. Maybe the filter is behind us, a rare fluke that let life emerge on Earth against impossible odds. Or worse, it's ahead of us, some catastrophic event every advanced civilization hits, like self-destruction through war or climate collapse. The filter could explain the silence, not because aliens don't exist, but because they don't survive long enough to be heard. It's a chilling thought, turning every breakthrough in space exploration into a test. Are we the exception or just next in line? Then there's the zoo hypothesis, the idea that advanced civilizations know we're here but choose not to interfere, leaving Earth as a kind of cosmic nature preserve. Picture an interstellar prime directive where they watch from a distance until we're ready. Or perhaps the universe is simply too big and signals get lost in the noise. Imagine two people stranded on opposite sides of the ocean, shouting into storms. Chances are they'll never hear each other. Even our own radio signals have barely traveled 100 light years, a drop in the galactic bucket. Science fiction loves to play with these theories. Childhood's End envisions humanity as latecomers to a universe where greater beings have moved beyond physical forms. The three-body problem warns that broadcasting our location might invite disaster, turning the paradox into a survival strategy. These stories aren't just entertainment, they're thought experiments, helping us grapple with questions too big for labs or equations. But here's the twist: the silence might not be ominous. It could mean we're among the first, that the universe is still waking up to the idea of life. Or maybe we're looking for the wrong things, like expecting smoke signals in the age of fiber optics, new telescopes scanning for technosignatures, pollution, megastructures, even artificial light on exoplanets could rewrite the paradox tomorrow. The Fermi Paradox doesn't just ask about aliens, it holds up a mirror, forcing us to confront our own fragility and potential. Are we alone because life is fleeting, or because it's just beginning? The answer, when it comes, won't just solve a puzzle, it will tell us who we are in the story of the cosmos. Picture a single point, smaller than an atom, containing all the energy and matter that would one day become galaxies, stars, and you. Then, in less time than it takes to blink, that point explodes outward, not just expanding, but stretching space itself faster than light could chase it. This is cosmic inflation, the universe's first and most dramatic growth spurt, a burst of expansion so violent it defies intuition. In a trillionth of a second, the cosmos swelled from quantum scales to something the size of a grapefruit, smoothing out wrinkles in spacetime like a master ironing out cosmic fabric. The evidence for this wild idea lies in the cosmic microwave background, the afterglow of the Big Bang. When satellites like Planck mapped its faint whispers, they found a pattern nearly flawless in its uniformity. No hotspots, no dense clusters, just a sea of sameness stretching across the sky. Inflation explains this perfection. The universe ballooned so quickly that any irregularities were stretched into oblivion, leaving behind a canvas smoother than glass. But look closer, and you'll spot microscopic ripples in that canvas, quantum fluctuations blown up to cosmic proportions during inflation. These tiny wrinkles became the seeds of everything: galaxies, galaxy clusters, the vast web of matter we see today. Without them, the universe would be a featureless void. What powered this explosive birth? Theorists point to a mysterious field called the inflaton, a kind of cosmic fuel that drove expansion until it decayed, releasing its energy as matter and radiation. It's speculative, yes, but the math holds. Inflation solves puzzles no other theory can touch, like why the universe appears flat, or why we've never found magnetic monopoles. Still, the details are hazy. Was inflation a one-time event, or does it happen endlessly, spawning bubble universes with different laws of physics? Some models suggest our entire cosmos is just one bubble in an infinite froth of realities, each with its own unique history. The poetry of this moment isn't lost on storytellers. The Hindu Rig Veda describes creation as a golden womb bursting forth, while the Maori speak of Tikor, the void that separated into light and form. Even modern physicists borrow lyrical language, calling inflation the ultimate free lunch, a universe born from nothing but quantum potential. And perhaps that's the most staggering part. The idea that everything we know, from the Andromeda galaxy to the phone in your hand, traces back to a fluctuation smaller than a proton, amplified by the universe's first breath. Inflation isn't just a theory about the past, it's a lens for understanding the universe's fate. If inflation happened once, could it happen again? Some models predict a big rip, where dark energy accelerates expansion until even atoms are torn apart. Others imagine cyclical universes collapsing and reborn in endless loops. Whatever the truth, inflation reminds us that the cosmos is dynamic, unpredictable, and far stranger than our everyday experience suggests. The universe didn't just begin, it erupted, and we're still riding the shockwave. Two particles born from the same quantum event fly apart, one to a lab on Earth, the other to a satellite orbiting Jupiter. Change the spin of the first, and instantly, without any signal or delay, the second particle responds as if they're still touching. This isn't telepathy or magic, it's quantum entanglement, a phenomenon so bizarre that even Einstein recoiled from its implications, dismissing it as spooky action at a distance. Yet, decades of experiments have confirmed it's real. In labs from Vienna to Shanghai, scientists have entangled particles across distances that would take light years to cross, proving that the universe has a hidden wiring we're only beginning to map. The mechanics are as elegant as they are unsettling. When particles become entangled, they lose their individual identities, merging into a single quantum state. Measure one, and you instantly define its partner's properties, no matter how far apart they've traveled. This isn't just faster than light communication, it's outside time altogether, a correlation that defies our everyday understanding of cause and effect. The universe, it seems, keeps shortcuts in its back pocket, threads of connection woven into the fabric of space-time itself. Practical applications are already emerging from this quantum weirdness. Quantum computers like Google's Sycamore use entangled qubits to perform calculations that would take classical supercomputers millennia. Secure communication networks, like China's Misha satellite, leverage entanglement to create unhackable encryption keys, where any eavesdropper would instantly break the delicate quantum link. Even astronomy is getting a boost. Entangled photons could one day let telescopes act as a single, planet-sized instrument, peering deeper into space than ever before. But the implications stretch far beyond technology. Philosophers and mystics have long argued that everything in the universe is interconnected, from ancient Hindu teachings about the oneness of Brahman to modern ecological theories of Gaia. Quantum entanglement doesn't prove these ideas, but it does offer a tantalizing parallel, a universe where separation might be an illusion, where the boundaries between you and the cosmos are far blurrier than Newtonian physics suggested. The debate over what entanglement means is far from settled. Some interpretations, like the Copenhagen school, insist particles have no definite state until observed, implying reality is participatory, shaped by measurement. Others, like pilot wave theory, suggest hidden variables guide the particles' dance, while the many worlds interpretation claims every quantum decision spawns new universes. Each view paints a radically different picture of existence, from a cosmos built on randomness to one branching endlessly into alternate timelines. Artists and writers have seized on entanglement as a metaphor for human connection. In his Dark Materials, Philip Pullman's subtle knife cuts between worlds, echoing the non-locality of quantum links. Rumi's poetry, "You are not a drop in the ocean, you are the entire ocean in a drop," resonates with the idea that particles might carry echoes of their partners across light years. These aren't scientific claims, of course, but they reflect a truth science is now grappling with, that the universe's deepest laws might be stranger, more intimate than we ever dreamed. At its heart, entanglement forces us to confront a humbling possibility. The universe doesn't owe us intuitive explanations. It operates by rules that might forever hover just beyond human comprehension, leaving us to navigate the borderlands between knowledge and wonder. Whether you see it as a mathematical curiosity or a glimpse of cosmic unity, one thing's certain: reality is far richer, far weirder than our ancestors dared to imagine. And that's a mystery worth unraveling. Somewhere beyond the Milky Way's starry veil, in a patch of sky obscured by our own galaxy's dust and gas, an invisible titan exerts its pull. Every galaxy in our cosmic neighborhood, the Milky Way, Andromeda, even the distant Virgo cluster, is drifting toward this enigmatic point like moths to a flame. Astronomers call it the Great Attractor, and its gravitational grip is so strong it bends the motion of hundreds of thousands of galaxies, steering them through the void at over 1 million miles per hour. Yet despite its colossal influence, we've never seen it directly. It's as if the universe is playing a game of hide and seek, dangling clues just out of reach. The first hints emerged in the 1970s when astronomers noticed something odd. Galaxies in our local supercluster weren't just drifting apart with the universe's expansion. They were all streaming toward the same unseen destination. Later studies revealed the culprit's approximate location, roughly 250 million light-years away in the constellation Centaurus. But there was a problem. The Great Attractor lay directly behind the Milky Way's crowded disk, a region so choked with dust and stars that telescopes struggled to peer through. It was like standing in a crowded room, trying to spot a distant landmark through a forest of raised arms. What we've pieced together is both astonishing and humbling. The Great Attractor isn't a single monolithic structure, but likely a dense knot of galaxies, perhaps hundreds of thousands of them, bound together by gravity into a supercluster of staggering mass. X-ray observations hint at vast clouds of hot gas swirling between these galaxies, and infrared surveys have peeled back the Milky Way's veil just enough to spot a few of the brightest members, like the Norma cluster. But the full picture remains frustratingly blurry. Some theorists even speculate there could be something more exotic at work, a concentration of dark matter so dense it warps spacetime like a cosmic whirlpool, or a gravitational echo from an era before the Big Bang. Science fiction loves to spin wilder tales. Arthur C. Clarke's Rendezvous with Rama imagined the Great Attractor as an alien artifact, a beacon drawing civilizations together for some unfathomable purpose. The video game Destiny turned it into a trap set by ancient gods. These stories tap into a deeper truth. The unknown terrifies and fascinates us in equal measure. Because the Great Attractor isn't just pulling galaxies, it's pulling our curiosity, reminding us that for every mystery we solve, the universe unveils 10 more. Astronomers aren't giving up. New tools like the James Webb Space Telescope and next-generation radio arrays are mapping the hidden region in unprecedented detail, while simulations trace the gravitational ripples that could reveal the attractor's true scale. What they find might rewrite our place in the cosmos. After all, if we're being pulled towards something we can't fully see, what else is out there just beyond our sight? The Great Attractor is more than a scientific puzzle. It's a cosmic compass pointing not just to a destination, but to all the wonders we've yet to discover. Time isn't the steady, universal metronome we imagine. Einstein's revelation that gravity doesn't just bend space, but time itself, shattered the illusion of a cosmic clock ticking the same for everyone. Picture this: an atomic clock placed on Earth's surface will tick ever so slightly slower than one in orbit. The difference is minuscule, just a few billionths of a second per day. But without accounting for this drift, GPS satellites would misplace your location by miles within minutes. It's a quiet, everyday proof that time is fluid, shaped by the mass it brushes against. Now, take that effect and amplify it near a black hole, where gravity becomes a tidal force twisting the very fabric of reality. In Interstellar, the cruise hour on Miller's planet costs them 23 years back on the ship. While Hollywood took creative liberties, the science behind it is sound. The closer you hover to a black hole's event horizon, the more time stretches like taffy. For an outside observer, your movements would slow to a crawl, your signals redshifted into oblivion. Yet for you, time would feel normal right up until the moment gravity's grip became irreversible. This isn't just theoretical. Astronomers have watched stars skirting the supermassive black hole at our galaxy's center, their light stretched and slowed exactly as relativity predicts. But time dilation isn't just about extreme cosmic environments. It's woven into the mundane too. Fly around the world in a jet, and you'll age a fraction of a second less than those on the ground, a phenomenon verified with atomic clocks in the 1970s. Even your head ages faster than your feet, thanks to Earth's gravity pulling harder the closer you are to its core. The differences are imperceptible, but they whisper a profound truth. Time is personal, a private rhythm dancing to gravity's tune. Philosophers and poets have long wrestled with time's paradoxes. St. Augustine called it a threefold present: memory, attention, and expectation collapsing into now. T.S. Eliot wrote of moments in and out of time, while Borges imagined a library where every possible future already exists. Science gives these metaphors teeth. If time bends, then the past, present, and future might not be as fixed as they feel. Some physicists, like Carlo Rovelli, argue time is an emergent property, a collective illusion born from quantum interactions. Others see it as a dimension we're perpetually sliding through, like a fish carried by a river it cannot see. Perhaps the most haunting implication is what this says about mortality. If time is relative, then a human lifespan isn't a fixed span. It's a variable, stretched or compressed by where and how you live it. A civilization orbiting a black hole could witness the heat death of the universe in what feels like generations. Meanwhile, a photon traveling at light speed experiences no time at all. From its perspective, it's emitted and absorbed in the same instant, even if billions of years pass in between. Time dilation doesn't just challenge our clocks, it challenges our stories, forcing us to ask, what does it mean to live when now is never the same for everyone? From atomic clocks to black holes, from jet lag to the death of stars, time's fluidity is a reminder the universe isn't just stranger than we imagine, but stranger than we can imagine. And in that strangeness lies a curious comfort. However tightly we clutch our schedules and calendars, time was never ours to command. It's a cosmic collaborator, bending to gravity's will, inviting us to see every ticking second not as a given, but as a gift. Imagine a planet so close to its star that its oceans boil away into space, and another so distant it's frozen solid beneath miles of ice. Now picture a world just right, where sunlight kisses the surface gently enough to keep water liquid, pooling in lakes, flowing in rivers, perhaps even filling vast, life-giving seas. This sweet spot is the Goldilocks Zone, the cosmic real estate where the universe allows its most fragile miracle to unfold, the possibility of life as we know it. Earth didn't win this perfect orbit by chance. Our sun's habitable zone is a narrow ribbon, and we're nestled snugly within it. Venus, just a bit closer, is a blistering hellscape with runaway greenhouse gases. Mars, a tad farther out, is a frozen desert. But here, in this delicate balance, chemistry dances toward biology. Water stays liquid, proteins fold, and molecules link into chains that might one day whisper, "I am." It's a balance so precise that even a 5% shift in Earth's distance from the Sun could have rendered our planet uninhabitable. The search for other Goldilocks worlds has turned up astonishing candidates. Kepler 186f, orbiting a dim red dwarf, basks in perpetual twilight, while TRAPPIST-1e, with its 7 sibling planets, might host underground oceans warmed by tidal forces. But the zone isn't just about distance, it's a symphony of factors. A planet's atmosphere, magnetic field, even the stability of its star all play a role. Tidally locked worlds with one face permanently scorched and the other frozen might still cradle life in the thin twilight between. This quest isn't just about finding Earth twins. It's about redefining what habitable even means. Europa, Jupiter's icy moon, hides a subsurface ocean heated by gravitational friction far outside the traditional zone. Methane lakes on Titan hint at exotic biochemistries where water isn't the solvent. The universe, it seems, is more creative than our textbooks. Every discovery stretches the boundaries, asking, are we the rule or the exception? Scientists and dreamers alike are drawn to this question. Carl Sagan once mused that the absence of evidence for life beyond Earth is either a hint of our uniqueness or a sign of how little we've searched. The Goldilocks Zone embodies that tension between the cold calculus of probability and the warm hope that life might be written into the fabric of the cosmos. After all, if water worlds are common and chemistry tends toward complexity, then perhaps biology isn't a fluke. Perhaps it's the universe waking up to itself, one planet at a time. And so we keep looking. Telescopes like James Webb analyze the atmospheres of distant worlds, hunting for oxygen, methane, even industrial pollutants. Future missions will probe icy moons for microbial hitchhikers. Each discovery, whether a barren rock or a world teeming with possibilities, refines the equation. Because the Goldilocks Zone isn't just a place, it's a promise that somewhere in the vast dark, another spark might flicker, another story might begin. And in that promise, we find not just answers about them, but about us. There comes a moment in a star's life when the delicate balance between gravity's inward pull and the outward pressure of nuclear fusion shatters. For massive stars, this isn't a quiet fade, it's a detonation of unimaginable violence, a supernova so brilliant it can outshine entire galaxies. In less than a second, the collapsing core rebounds with the force of 1 billion suns, hurling stellar material into space at nearly 1/10 the speed of light. The shockwave alone could vaporize entire planetary systems, yet within that chaos lies the universe's greatest alchemy. These explosions are cosmic forges, the only natural furnaces hot enough to create elements heavier than iron. Gold in your wedding ring, forged in a supernova's heart, the uranium powering nuclear reactors, born from a dying star's last breath. Even the calcium in your bones and the iodine in your thyroid were once stardust scattered across light years by these cataclysms. Every time you take a breath, you're inhaling atoms that survived a stellar explosion billions of years ago. We are, quite literally, made of star stuff, recycled remnants of celestial violence. Astronomers treasure supernova as natural laboratories. The famous SN 1987A, visible even to the naked eye, confirmed theories about neutrino emissions and revealed how shockwaves trigger new star formation in their wake. Today, automated sky surveys catch hundreds yearly, each a Rosetta Stone for decoding stellar life cycles. Some, like Type Ia supernova, burn so predictably they're used as standard candles to measure cosmic distances, helping us map the universe's accelerating expansion. Others, like hypernova, produce gamma-ray bursts so intense they could sterilize planets halfway across the galaxy. Humanity has long sensed the mythic weight of these events. The Crab Nebula, a supernova remnant recorded by Chinese astronomers in 1054, was seen as an omen, a guest star that disrupted the celestial order. Norse myth spoke of Ragnarok, where stars would fall from heaven before a new world emerged. Modern telescopes show these stories weren't entirely wrong. The Veil Nebula's delicate filaments, glowing in Hubble's images, are the shredded remains of a star that died 20,000 years ago, its debris now seeding new generations of stars and planets. What makes supernova transcendent isn't just their destructive power, but their creative potential. The pillars of creation, those iconic towers in the Eagle Nebula, were likely sculpted by shock waves from ancient supernova. The same blast that ends one star's life compresses nearby gas clouds, triggering the birth of others. It's a reminder that in the cosmos, death and creation are two sides of the same coin, a cycle written into the laws of physics itself. When we look at a supernova, we're witnessing the universe's way of recycling, of taking what was and forging it into what could be. Perhaps that's why these explosions captivate us so deeply. They're not just astrophysical events, they're cosmic metaphors. In their light, we see our own origins and eventual fate, the knowledge that every ending carries the seeds of a new beginning. The next time you gaze at the night sky, remember, some of those twinkling lights are destined to explode, and in their ashes, new worlds, and maybe even new life, will one day rise. Dark energy is the universe's best-kept secret, a force so dominant it shapes cosmic destiny, yet so elusive we've never directly detected it. Picture a loaf of raisin bread baking in an oven. As the dough expands, every raisin moves away from the others. That's how astronomers once imagined cosmic expansion, galaxies drifting apart as space stretches. But in the late 1990s, two teams studying distant supernova made a chilling discovery. The universe wasn't just expanding, it was accelerating, as if some invisible hand had turned up the oven's heat. The culprit, dark energy, a repulsive force that makes up 68% of everything in existence, yet defies every tool we've built to understand it. What makes dark energy so baffling is how it flips gravity's script. Matter pulls, but dark energy pushes, and over cosmic distances, its push is winning. Galaxies once bound by gravity's embrace are now being wrenched apart, their light stretched into infrared oblivion. If this continues, billions of years from now, the Milky Way will stand alone in an ocean of darkness. Every other galaxy vanished beyond the horizon of visibility. Cosmologists call this the Big Freeze, a future so desolate it makes black holes seem hospitable. The leading theory pins dark energy on the cosmological constant, an energy intrinsic to empty space itself. Einstein proposed it in 1917 to balance his equations, then famously called it his greatest blunder when expansion was discovered, yet it might have been his greatest insight after all. Quantum physics suggests that even a vacuum bubbles with particles popping in and out of existence, each lending space a tiny energy. But here's the catch. When scientists tally up these contributions, the predicted dark energy is 10 to the power of 120 times stronger than observed. It's the worst mismatch in science, a number so absurd it hints at a gaping hole in our understanding. Alternative explanations abound. Some theorists propose dark energy isn't constant but evolves, a relic of an ancient field that once powered cosmic inflation. Others suggest gravity itself behaves differently across vast distances, a tweak that would rewrite Einstein's relativity. Then there's the spine-tingling possibility that dark energy is evidence of extra dimensions, their unseen geometry leaking into ours. Each idea is a shot in the dark, but that's the thrill. Dark energy isn't just a puzzle to solve, but a compass pointing toward deeper laws of physics we've yet to uncover. Artists and philosophers have long sensed the poetry in this mystery. The ancient Stoics spoke of the pneuma, a breath that animated the cosmos. Modern poets like Tracy K. Smith write of dark energy as the universe's sigh, an exhale that carries galaxies like dandelion seeds. Even the language of science echoes this, terms like phantom energy and quintessence, blur the line between physics and myth. Perhaps that's why dark energy captivates us. It's not just about equations, it's about confronting the sublime, the realization that everything we see, stars, planets, even our own bodies, is just froth on a dark ocean whose currents we're only beginning to trace. The discovery of dark energy was a wake-up call. For centuries, we assumed the universe's fate was a simple tug of war between expansion and gravity. Now we know there's a third player, one tipping the scales toward an outcome stranger than fiction. Whether it's a property of space, a new force, or a sign of deeper layers to reality, dark energy guarantees one thing: the cosmos still has surprises up its sleeve. And in that uncertainty lies the most exhilarating promise of all, that the universe isn't just expanding but evolving, and with it, our understanding of what's possible. In a quiet room in West Virginia in 1961, astronomer Frank Drake scribbled 7 terms on a chalkboard, not realizing he was about to create the most debated equation in the search for alien life. The Drake equation seems simple at first glance, just a chain of probabilities multiplied together. But behind each variable lies a universe of unknowns. Start with the number of stars born yearly in our galaxy, then ask what fraction have planets. Narrow it further, how many of those planets sit in the habitable zone? Then comes the real mystery: how often does life emerge? And if it does, how often does it evolve intelligence? Each term is a door cracked open just enough to let imagination rush through. What makes this equation extraordinary isn't its precision, it's the way it turns philosophy into numbers. Carl Sagan estimated the final product could range from a single lonely civilization, us, to millions, depending on whether you're an optimist or pessimist about life's odds. Take the term F sub I, the fraction of life-bearing worlds where intelligence arises. Some biologists argue intelligence is a fluke, that evolution favors crabs and fungi over thinkers. Others point to Earth's multiple intelligent species, dolphins, octopuses, corvids, as proof that nature stumbles onto cleverness more often than we think. The equation doesn't settle these debates, it gives them structure, turning "what if" into "how many." Pop culture loves playing with these variables. Star Trek assumes F sub C, the fraction of civilizations that develop interstellar communication, is high, painting a galaxy buzzing with warp drives and diplomacy. Arrival, on the other hand, lingers on L, the average lifespan of a technological society, asking whether civilizations inevitably self-destruct or learn to endure. Even the X-Files plays with the equation's gaps, suggesting governments hide the truth because the real answer is too terrifying or too disappointing. But the Drake equation's true power lies in its humility. By quantifying our ignorance, it reveals how much we have left to learn. When SETI radio telescopes scan the skies, they're not just hunting for aliens, they're testing assumptions buried in Drake's terms. The discovery of extremophiles life thriving in boiling vents or Antarctic ice suggests F sub L, the fraction of habitable planets where life appears, might be high. The silence of the cosmos, though, hints that L could be tragically small, that technological civilizations might flicker out like candles in a storm. Perhaps that's why this equation endures. It's not a calculator, it's a mirror. However you fill in the blanks, the answer tells you something about how you see humanity's place in the cosmos. Are we a statistical inevitability or a cosmic accident? A fleeting spark or the first ember of something greater? The numbers won't settle that, but the act of asking changes us. Every time we point a telescope at a star, we're not just searching for aliens, we're deciding what kind of universe we want to live in. Pulsars are the universe's most precise timekeepers, stellar remnants spinning so fast they whip beams of radiation across space like a cosmic lighthouse. When Jocelyn Bell Burnell first detected their rhythmic pulses in 1967, the signal was so unnervingly regular that her team jokingly labeled it LGM-1, short for Little Green Men. The truth was even stranger. A city-sized neutron star heavier than our Sun, spinning hundreds of times per second, its magnetic poles sweeping the sky with radio waves like a celestial strobe light. What makes pulsars extraordinary isn't just their speed, it's their precision. The Crab pulsar, born from a supernova observed in 1054, spins 30 times a second with a consistency that rivals atomic clocks. Millisecond pulsars, accelerated by stolen stellar material, achieve even more staggering regularity, their pulses arriving with nanosecond accuracy. Astronomers exploit this reliability as a natural GPS, using pulsar timing arrays to detect gravitational waves ripples in spacetime from colliding black holes, by measuring how these waves subtly alter the arrival time of pulses across the galaxy. But pulsars are more than scientific tools. Their pulses have inspired composers to translate cosmic rhythms into music, turning electromagnetic beats into symphonies. Visual artists render them as spinning diamonds, their beams cutting through nebulous clouds. Even their formation is a spectacle. When a massive star collapses into a neutron star, its magnetic field intensifies 1 trillion-fold, launching jets of particles that glow in X-rays and gamma rays. The Vela pulsar, for instance, dances with auroras visible in space, its charged particles painting the sky near light speed. Yet for all their clockwork perfection, pulsars hide violent secrets. Some, like the Black Widow pulsar, orbit so closely to a companion star that their radiation slowly evaporates it, a stellar vampirism that leaves behind a ghostly husk. Others, like the Magnificent Seven, glow in X-rays without pulsing, their magnetic fields so strong they've trapped their own atmospheres in crystalline crusts. And then there are the anomalies pulsars like PSRB 1937+21, whose spin occasionally hiccups, as if something inside is cracking and rearranging under pressures we can't replicate on Earth. Perhaps the most profound lesson pulsars teach is about impermanence. Even these paragons of stability slow over time, their energy bleeding into space as gravitational waves and radiation. In 1 billion years, today's millisecond pulsars will become silent neutron stars, their beams too faint to detect. But for now, their pulses cut through the dark like Morse code, reminding us that even in chaos, the universe writes its own kind of order, one precise flash at a time. Beyond the last whispers of sunlight, where the warmth of our star fades to near nothingness, lies a kingdom of ice and shadow, the Oort Cloud. Picture a vast spherical shell of frozen relics stretching nearly a light year from the sun, a graveyard of primordial rubble left over from the solar system's violent birth. These aren't just chunks of ice, they're time travelers, each holding chemical blueprints from an era before planets even existed. When one occasionally tumbles inward, pulled by the gravity of passing stars, we see it as a comet, a glowing visitor with a tale of vaporized history. What makes the Oort Cloud extraordinary isn't just its distance, but its patience. These icy bodies have drifted unchanged for 4.6 billion years, their chemistry untouched by the heat and collisions that reshaped the inner solar system. A single comet like Hale-Bopp, which lit up skies in 1997, carries molecules older than Earth itself, water laced with deuterium, organic compounds that might have seeded our oceans, even amino acids, the building blocks of life. Studying them is like cracking open a frozen textbook, its pages written in the language of the cosmos' infancy. Yet for all its scientific value, the Oort Cloud remains frustratingly out of reach. Voyager 1, the farthest human-made object from Earth, won't brush its outer edges for another 300 years. Instead, astronomers piece together its secrets by tracking comet trajectories, simulating its formation, and listening for the faint radio whispers of molecules in distant molecular clouds. Some theories suggest the Oort Cloud isn't even entirely ours, that it's laced with interstellar interlopers, icy nomads captured as the sun wandered through the galaxy. Science fiction adores this unseen frontier. In Arthur C. Clarke's 2061 Odyssey 3, the Oort Cloud hides a monolith-activated supercomet, its destiny tied to humanity's evolution. The Expanse imagines it as a lawless haven for rebels and rogue scientists, exploiting its vastness to evade detection. These stories tap into a deeper truth. The Oort Cloud is the ultimate wilderness, a place so remote it defies ownership, where the rules of the inner solar system no longer apply. But the real magic lies in what it represents: a boundary not just of space but of imagination. The Oort Cloud reminds us that our solar system doesn't end with Pluto or even the Kuiper Belt. It stretches into the abyss, a ghostly halo of memories from a time when the sun was just another newborn star in a crowded nursery. Every comet that visits us is a messenger from that forgotten age, a fleeting glimpse into the chaos that shaped our cosmic home. And in their icy hearts they carry a silent question: how much of our story is still waiting, frozen in the dark? Einstein's equations painted a universe far stranger than he ever imagined, one where space-time could fold like paper, creating tunnels between distant points. These hypothetical passages, known as wormholes, aren't just science fiction. The math permits them. Picture a black hole's singularity not as a dead end, but as a bridge, a cosmic subway connecting two locations light years apart in a single step. Theoretically, a traveler could enter one mouth of the wormhole and emerge from the other moments later, bypassing the vast emptiness between. It's the ultimate shortcut, a loophole in the universe's speed limit that even light can't touch. But here's the catch: wormholes, if they exist at all, would be catastrophically unstable. Without some form of exotic matter, a substance with negative energy density to prop open the throat, the tunnel would collapse faster than you could say a black hole. The closest we've come to this phantom material is the Casimir effect, where quantum fluctuations between two plates create a negative energy field. Yet the amounts needed to stabilize a traversable wormhole are beyond anything we can engineer, let alone comprehend. Some theorists, like Kip Thorne, suggest advanced civilizations might harness this technology, while others argue the laws of physics outright forbid it. Science fiction, of course, has run wild with the idea. Stargate turned wormholes into ancient highways for interstellar travel, while Interstellar's Gargantua featured a navigable wormhole placed near Saturn by mysterious, higher-dimensional beings. These stories gloss over the lethal tides of gravity, the spaghettification that would shred any human traveler, but they capture the deeper allure wormholes represent: hope. Hope that the universe isn't just a cold, empty prison, but a place riddled with secret doors waiting for the right key. The debate among physicists isn't just about feasibility, it's about philosophy. If wormholes can exist, even briefly, do they imply a universe more interconnected than we dreamed? Could they be time machines with one end accelerated to near light speed, creating a bridge between eras? Hawking's chronology protection conjecture argues nature abhors time loops, but the math remains tantalizingly ambiguous. Meanwhile, quantum entanglements, spooky action at a distance, hints at hidden threads binding the cosmos. Could wormholes be their macroscopic cousins? Perhaps the most profound question isn't whether wormholes exist, but what their possibility tells us about reality. They blur the line between physics and fantasy, between the known and the unimaginable. Every equation that permits them whispers a challenge. the universe is under no obligation to make sense to us. Yet here we are, mapping black holes, probing quantum foam, and daring to ask what if the stars aren't so far away after all. In the static of an old television set, between the channels where nothing seems to be broadcasting, there's a secret hiding in plain sight, a faint hiss that isn't random noise at all, but the universe's oldest message. This is the cosmic microwave background, the afterglow of creation itself, lingering like the warmth of a campfire long after the flames have died. It's light from a time before stars, before galaxies, when the cosmos was just a glowing fog of plasma, hot and dense as soup. Then, 380,000 years after the Big Bang, everything changed. The universe cooled enough for atoms to form, and light, once trapped in the chaos, finally broke free, streaming outward in every direction. That light is still traveling today, stretched by the expansion of space into microwaves, carrying with it a fingerprint of the universe's fiery infancy. The discovery of this cosmic whisper was pure serendipity. In 1965, Bell Labs astronomers Arno Penzias and Robert Wilson were troubleshooting a persistent radio hiss in their antenna, one that wouldn't go away no matter how many pigeons they cleared from the equipment. That stubborn noise turned out to be the CMB, a discovery that won them the Nobel Prize and cemented the Big Bang as the leading theory of cosmic origins. But the real magic lies in the details. Maps from satellites like COBE, WMAP, and Planck reveal the CMB isn't perfectly uniform. It's mottled with tiny temperature variations, fluctuations no larger than 1 part in 100,000. These imperfections are cosmic gold, the seeds from which galaxies and superclusters would later grow. Gravity amplified those slight density differences over billions of years, sculpting the vast web of matter we see today. What's astonishing is how much we've decoded from this primordial static. The CMB's patterns tell us the universe is geometrically flat, its contents finely balanced between dark matter, dark energy, and ordinary matter. They hint at cosmic inflation, that explosive expansion in the universe's first moments, which stretched quantum fluctuations into the large-scale structures we inherit. Some researchers even claim to have spotted anomalies, unexpected cold spots or asymmetries, that could point to parallel universes or a cosmos far stranger than we've imagined. Yet for all we've learned, the CMB raises deeper questions. What sparked the Big Bang? Was there a before? Or does time itself begin there? The CMB is the ultimate boundary, a curtain drawn across the earliest chapters of existence. Philosophers and artists have long been drawn to this echo. Composer John Cage incorporated cosmic static into his avant-garde works, calling it the sound of the universe thinking. Poets liken the CMB to a palimpsest, a parchment where the first words of creation are still faintly visible beneath newer layers. Even spiritual traditions find resonance. The Hindu Rigveda's Nasadiya Sukta describes a time before time when darkness was hidden by darkness, a description eerily reminiscent of the universe's primordial fog. The cosmic microwave background isn't just radiation. It's a reminder that the universe has a memory, that every one of us is bathed in the afterglow of an event older than atoms. When you tune an old radio between stations, you're not just hearing noise, you're listening to the universe's first breath, a whisper from the dawn of everything, still telling its story after all this time. At the smallest scales imaginable, far beyond the reach of even our most powerful microscopes, the universe may not be made of points or particles, but of tiny, vibrating strings. Picture a guitar string plucked to play different notes. Now shrink that string down a billion times until it's smaller than an atom. According to string theory, these minuscule filaments of energy aren't just hypothetical. They could be the fundamental building blocks of everything. The pitch of their vibrations determines what they become. One note might manifest as an electron, another as a quark, and yet another as the photon carrying light itself. In this radical vision, reality isn't built from static dots on a cosmic blueprint. It's a dynamic, humming orchestra, with every particle a distinct tone in an 11-dimensional symphony. For centuries, poets and philosophers have sensed music in the cosmos. Pythagoras spoke of the music of the spheres, Kepler mapped planetary orbits to harmonic intervals, and Einstein wondered if God had any choice in creating the universe's laws. String theory gives these intuitions startling new weight. The mathematics behind it suggests that the four forces we know, gravity, electromagnetism, and the nuclear forces, might simply be different octaves of the same underlying melody. Even space-time itself could emerge from the interplay of these strings, like the resonance of a violin's body shaping the notes it plays. The theory doesn't just unify physics, it turns the universe into a grand composition, where the laws of nature are sheet music written in the language of higher dimensions. Yet for all its elegance, string theory remains frustratingly out of reach. The strings themselves are thought to be so tiny that probing them directly would require energies 1 trillion times beyond what our particle colliders can muster. Worse, the theory predicts not 1 but 10 to the power of 500 possible universes, each with its own physical constant, a multiverse, so vast it makes testing any single version nearly impossible. Critics argue this lack of falsifiability pushes string theory into the realm of metaphysics, while defenders counter that its mathematical beauty is too compelling to ignore. After all, general relativity was once considered abstract and untestable until starlight bending around the sun proved Einstein right. Artists and musicians have embraced string theory's metaphors. Composer John Cage wrote pieces based on cosmic randomness, while physicist Brian Greene's book, The Elegant Universe, inspired a symphony where string vibrations were translated into musical notes. There's a deeper resonance here, too. If the universe truly is a vibrational tapestry, then the ancient idea of as above, so below takes on new meaning. The same mathematics describing vibrating strings also governs the harmonics of a Stradivarius or the orbital resonances of planets. Could this be coincidence or a hint that music and physics share a common root? String theory's boldest claim isn't just about strings, it's about dimensions. To make the equations work, the universe might need 7 hidden spatial dimensions beyond the 3 we experience, curled up so tightly we never notice them. Imagine an ant walking along a telephone wire. From afar, the wire seems one-dimensional, but up close, it has a circular dimension wrapping around it. In string theory's hidden dimensions, the geometry could determine the tuning of our universe's laws, like the shape of a flute dictating its scale. Some models even suggest these dimensions aren't static. They could vibrate, collapse, or reconfigure, rewriting physics in cosmic upheavals we'd perceive as new Big Bangs. Whether string theory ever finds experimental proof, it's already reshaped how we see reality. It challenges us to think beyond particles and forces, to envision a universe where matter, energy, and even time are emergent harmonies. The theory's greatest gift might not be answers but questions. Is the cosmos a soloist or a chorus? Are we listeners or notes in the song ourselves? For now, the strings keep vibrating, their music just beyond our hearing, waiting for the day we learn to tune in. The idea that Earth might be alive isn't just poetic fancy, it's a scientific hypothesis that rewires how we see our planet. When chemist James Lovelock first proposed the Gaia hypothesis in the 1970s, he wasn't gazing at forests or oceans for inspiration. He was working with NASA, designing instruments to detect life on Mars. Lovelock realized something profound. If life existed there, it wouldn't just inhabit the planet, it would change it. Earth's atmosphere, with its unstable mix of oxygen and methane, is practically a fingerprint of biology at work. Mars, by contrast, had an atmosphere in dead chemical equilibrium. That observation sparked a radical thought: what if Earth isn't just a rock hosting life, but a vast, self-regulating system where life and environment co-evolve like cells in a body? Take something as simple as ocean salinity. For billions of years, rivers have carried salt into the seas, yet the oceans never become too salty for life. Gaia suggests this isn't luck, it's regulation. Marine organisms may influence evaporation rates, while bacterial mats trap minerals before they reach the water. Even the planet's temperature appears suspiciously stable despite the sun growing 30% brighter since life began. Volcanic CO2, cloud formation, even the way plants release compounds to seed rainfall, all could be part of a planetary-scale dance, a kind of unconscious teamwork to keep conditions just right. Not everyone embraces Gaia as hard science. Critics argue it's closer to metaphor, that Earth's balance emerges from countless independent processes, not some grand collaboration. But the hypothesis has undeniably shaped climate research, framing the planet as an interconnected web where burning rainforests or melting permafrost aren't isolated events. They're symptoms of a system out of sync. This perspective birthed Earth system science, a field that studies feedback loops between ice sheets, ocean currents, and even microbes in soil. When we say, "save the planet," Gaia reminds us, we're not protecting an inert stage, but participating in a living performance. Artists and storytellers have stretched Gaia's implications to cosmic scales. Frank Herbert's Dune gave us Arrakis, a desert world whose spice cycles bind ecology and culture into a single destiny. In Avatar, Pandora's neural network mirrors Lovelock's vision, with trees acting as synapses in a global mind. Even beyond fiction, Gaia nudges us to ask, if Earth can behave like an organism, could other planets? Venus's runaway greenhouse effect might be a fever it couldn't break. Mars, frozen and barren, could be a biosphere that failed. When the James Webb Telescope analyzes exoplanet atmospheres, we're unconsciously hunting for Gaia's fingerprints, gases out of equilibrium, the chemical signatures of something alive. What makes Gaia endure isn't just its science, it's the story. For centuries, we've cast nature as either a machine to master or a goddess to worship. Gaia offers a third path, Earth as a dynamic partner, one we've only begun to understand. Whether literal truth or profound metaphor, it reshapes our role. We're not just inhabitants of this world, we're threads in its fabric capable of unraveling it or helping it heal. And if life elsewhere follows Gaia's rules, then every planet we find might not just host life. It might be alive, breathing in ways we're only learning to see. The universe hums with energy untapped, unfathomable, enough to power civilizations for eons. But how much of that energy could a species realistically harness? In 1964, Soviet astronomer Nikolai Kardashev gave us a ruler to measure such ambitions. His scale isn't about military might or artistic achievement, but raw power, the ability to command the cosmos itself. At its base, a Type I civilization has mastered its home planet, capturing all the sunlight that reaches its surface, controlling weather, perhaps even manipulating tectonics. That's roughly 10 to the power of 16 watts, 1,000 times more than humanity currently uses. We're not even Type I yet. By some estimates, we hover around Type 0.7, still burning fossilized sunlight like kindling while the stars pour their bounty into the void. Climbing the scale demands leaps of imagination. A Type Roman II civilization doesn't just use solar power, It builds around its star, perhaps constructing a Dyson swarm, a constellation of energy collectors encircling the sun like a hive. Picture this: trillions of orbiting panels, each the size of continents, siphoning a star's entire output. The energy here, 10 to the power of 26 watts. Such a society might rewrite stellar mechanics, prolonging their sun's life or igniting new ones. Science fiction loves this stage. Larry Niven's Ringworld imagines a ribbon encircling a star, while Star Trek's Federation taps into zero-point energy, edging toward Type Roman 3. And then there's the apex, Type Roman 3, galactic mastery. Here, energy consumption reaches 10 to the power of 36 watts, with civilizations spanning star clusters, harvesting black holes, or even creating universes in labs. The Milky Way would be their backyard, its 100 billion stars mere stepping stones. But how would we recognize such beings? Some scientists suggest searching for infrared signatures of Dyson swarms or gamma-ray bursts from star-powered engines. Others listen for neutrino patterns unnatural in their precision. So far, the silence is deafening, but perhaps we're scanning for the wrong signs, like ants trying to decode Wi-Fi. The Kardashev scale does more than rank aliens. It holds up a mirror to humanity. To reach even Type I, we'd need to solve fusion, unify global grids, and perhaps geoengineer climates. The challenges are as much social as technological. Could we cooperate on that scale without self-destructing? Some argue our energy gluttony might doom us before we reach the stars. Others see hope in exponential growth, Moore's law applied to clean energy, with solar efficiency and battery tech doubling every few years. But the scale's true gift is perspective. It frames our struggles and triumphs against a cosmic backdrop, where the difference between fire and starlight is just a matter of time. Whether we ascend the ladder or stall at its base, the Kardashev scale reminds us, energy isn't just about survival. It's about possibility, the chance to touch what lies beyond the next ridge of space-time, and to whisper back to the universe that we were here. On a quiet August night in 1977, a radio telescope in Ohio caught something extraordinary, a burst of radio waves so intense, so perfectly tuned to the frequency of hydrogen, that astronomer Jerry Amon circled it in red pen and scribbled, "Wow." Beside it, the signal lasted 72 seconds, blaring 30 times louder than the background noise of space, then vanished without a trace. Decades later, we still don't know what caused it. Was it a cosmic flare, a rogue comet, or the one time someone or something said hello? The WOW signal's mystery lies in its specificity. It hit exactly 1,420 megahertz, the resonant frequency of hydrogen, the universe's most abundant element. It's the logical channel for any civilization trying to announce its presence, a cosmic hailing frequency. Yet despite countless searches, it's never been heard again. Natural explanations abound. Perhaps it was a reflected signal from Earth-based radar bouncing off space debris, or an unusually intense burst from a passing comet's hydrogen cloud. But none fit the data perfectly. The signal's narrowband nature rules out most astrophysical phenomena, and its duration matches what we'd expect from a fixed source sweeping past the telescope's field of view. What makes this event endure isn't just the science, it's the way it plays with our longing. Carl Sagan once noted that absence of evidence isn't evidence of absence, and the WOW signal is the perfect embodiment of that tension. For SETI scientists, it's a tantalizing near miss, a reminder that the cosmos might be shouting while we're still learning to listen. For skeptics, it's a lesson in humility, a single anomaly in decades of silence. And for dreamers, it's a postcard from the void, a fleeting hint that we might not be the only ones wondering who else is out there. The signal's legacy lives on in modern searches. Breakthrough Listen, the most comprehensive SETI project to date, scans the same region of sky where the WOW signal originated, using instruments 1,000,000 times more sensitive than 1970s technology. Meanwhile, citizen scientists comb old data for overlooked patterns, hoping to find a second WOW hidden in the static. Even if the signal was natural, its cultural impact is undeniable. It's inspired novels like Contact, fueled conspiracy theories, and become a rallying cry for those who believe the universe is too big for solitude. Perhaps the WOW signal's greatest gift is the way it refuses closure. In a world where mysteries are increasingly solved by algorithms and satellites, here's one that still shrugs at our best tools. It's a Rorschach blot against the stars, revealing less about the cosmos and more about us, our hope, our skepticism, and our stubborn refusal to stop looking up. Whether it was aliens or just a cosmic quirk, one thing's certain: for 72 seconds in 1977, the universe had our undivided attention. And sometimes that's enough. Astrobiology doesn't just study life, it redefines what life could be. Picture a microbe thriving in boiling acid, or a bacterium buried under Antarctic ice, surviving on nothing but rock and radioactivity. These earthly extremophiles are the Rosetta Stone for astrobiologists, proving life can flourish in places once thought barren. If organisms can endure the scalding vents of Yellowstone or the crushing depths of the Mariana Trench, why not the methane lakes of Titan or the buried oceans of Enceladus? The rules of biology, it seems, are far more flexible than we ever imagined. Take Europa, Jupiter's icy moon. Beneath its frozen crust lies a global ocean kept liquid by tidal forces, with twice the water of Earth's seas. Hydrothermal vents on its seafloor might mirror those where life potentially began on our own planet, spewing minerals and warmth into the dark. NASA's upcoming Europa Clipper mission will scan for plumes erupting through the ice, hunting for organic molecules, chemical whispers of what might lurk below. But Europa isn't alone. Saturn's moon Enceladus shoots geysers of water into space, its icy grains laced with salts and even hydrogen, a potential energy source for microbial life. These aren't just moons, they're test tubes, offering clues to whether life is a cosmic fluke or an inevitability. Then there's the puzzle of Mars. Once a wet world with rivers and lakes, its rusty surface now holds tantalizing hints, methane spikes that could be geologic or biologic, complex organic molecules in ancient mudstones, even strange shapes in rocks that resemble fossilized microbes. A Perseverance rover is currently collecting samples for eventual return to Earth, where labs might finally answer whether the red planet ever hosted life. But Mars teaches another lesson: environments can change. If life existed there and died out, it's a sobering reminder that habitability isn't permanent. Science fiction loves painting aliens as humanoid or insectoid, but reality might be far weirder. Imagine silicon-based life forms breathing sulfur on Venus's clouds, or organisms with liquid methane for blood on Pluto. Astrobiologists entertain even wilder possibilities: dark matter life, quantum-scale beings, or even sentient stars. The only limit is the universe's creativity and our willingness to question assumptions. When Viking landers tested Martian soil in the 1970s, they looked for Earth-like metabolism. Had alien biology followed different rules, we might have missed it entirely. This search isn't just about microbes or intelligence, it's about our place in the cosmos. Finding even a single bacterium beyond Earth would mean life isn't a miracle, it's a process as natural as star formation. Conversely, silence would be equally profound, suggesting we might be alone in a universe that built a stage but never filled it. Either way, astrobiology bridges the cold equations of physics and the warmth of curiosity. It turns planets into pages and every mission a sentence in the greatest story ever told. Are we the universe's only way of knowing itself, or just one voice in a galactic chorus? The answer, when it comes, won't just rewrite textbooks, it'll redefine what it means to be alive. Imagine tweaking just one number in the fabric of reality, the strength of gravity, the charge of an electron, the nuclear forces binding atoms together. Shift any of these constants even slightly, and the universe as we know it unravels. Stars wouldn't form, molecules couldn't bond, and life would be impossible. Yet here we are, in a cosmos where these numbers align with eerie precision, as if the universe itself had dialed them in just right. This is the anthropic principle in action, the observation that the laws of physics appear perfectly calibrated to allow our existence. It's a realization that blurs the line between science and philosophy, forcing us to ask, are we the beneficiaries of cosmic luck, or is there something deeper at play? Consider the delicate balance of the cosmological constant, which governs the expansion of space. If it were slightly stronger, the universe would have expanded too rapidly for galaxies to form. Too weak, and gravity would have crushed everything back into a singularity. The odds of this value landing in the narrow sweet spot for life are astronomically small, like rolling a die and getting the same number a billion times in a row. Some physicists argue this fine-tuning points to a multiverse, a vast ensemble of universes, each with different physical constants, where we simply inhabit the one where the numbers lined up in our favor. In this view, we're not special, we're just the lucky winners of a cosmic lottery. Others see a different story. Theologians and philosophers have long interpreted this fine-tuning as evidence of intentional design, a universe crafted with purpose. Even secular thinkers like physicist Freeman Dyson have marveled at how the cosmos seems unusually hospitable to life, as if it were expecting us. But the anthropic principle doesn't settle the debate, it merely frames it. Whether you see the universe's constants as the result of infinite dice rolls or the signature of a deeper order, the principle holds up a mirror to our own existence. It doesn't tell us why we're here, only that the fact we're here to ask the question is itself a clue worth exploring. The implications ripple outward, touching everything from quantum mechanics to ethics. If the multiverse exists, does that diminish our significance, or does it make our improbable existence even more remarkable? If the universe truly is fine-tuned, what does that mean for our responsibility as its conscious inhabitants? These questions don't have easy answers, but they invite us to straddle the boundary between empirical observation and existential wonder. The anthropic principle isn't just a scientific idea, it's an invitation to marvel at the fact that we live in a universe capable of marveling at itself. And in that tension between chance and purpose, we find one of the most profound mysteries of all, the uncanny ability of the cosmos to not just exist, but to know itself through us. Beneath the serene surface of space-time, where gravity and quantum mechanics collide, lies a realm of chaos so profound it defies visualization. This is quantum foam, the hypothetical turbulence at the smallest possible scales, where the fabric of reality itself churns like a stormy sea. Picture the vacuum of space not as an empty stage, but as a boiling pot of virtual particles flickering into existence for mere fractions of a second before vanishing again. These aren't just mathematical quirks, they're the universe's way of balancing its books, borrowing energy from nothingness in bursts so brief they skirt the laws of physics. At scales a trillion times smaller than an atom, space-time might not be smooth at all, but a frothing, seething mess of wormholes, loops, and bubbles, a quantum foam where geometry itself loses meaning. The idea traces back to physicist John Wheeler in the 1950s, who imagined that if you could zoom in far enough, the orderly grid of Einstein's spacetime would dissolve into chaos. Gravity's rules would break down, with tiny regions of space curving wildly, pinching off into microscopic black holes or tunneling into other dimensions. It's as if the universe has a hidden layer, a subatomic underworld where the calm cosmos we know is built atop a frenzy of activity. This isn't just poetic speculation. Quantum foam emerges from attempts to reconcile general relativity with quantum mechanics, two pillars of physics that refuse to play nice. Until we have a theory of quantum gravity, foam remains a tantalizing placeholder, a mathematical hint that reality's foundations might be stranger than we dreamed. Science fiction loves to run with this concept. In Contact, Carl Sagan's aliens embed a message in the foam's fluctuations, turning the universe's smallest scales into a cosmic chalkboard. Doctor Who visualizes it as the time vortex, a turbulent river beneath spacetime's surface. These stories capture a deeper truth. Quantum foam isn't just about physics, it's about potential. Those virtual particles aren't merely random noise. They're evidence that the vacuum of space crackles with unspent energy, a reservoir of possibilities waiting to be tapped. In theory, if you could harness this zero-point energy, you'd unlock power beyond imagination. The catch: the foam's fluctuations happen at the Planck scale, distances so tiny that probing them would require accelerators larger than our solar system. Yet, even if we never observe quantum foam directly, its implications ripple outward. It challenges our intuition that space is passive and empty, suggesting instead that nothingness is alive with creative violence. It hints at a universe where the distinction between matter and emptiness blurs, where every cubic centimeter of empty space holds secrets we're only beginning to guess. And perhaps most tantalizingly, it raises a question that straddles science and philosophy. If space-time is fundamentally chaotic, why does it appear so smooth to us? Is our perception of order just an illusion, a statistical average of the chaos beneath? Quantum foam reminds us that reality has layers, and we've only scratched the surface. It's a humbling thought that the calm night sky above us, with its predictable orbits and steady stars, might rest atop a maelstrom of quantum uncertainty. Whether the foam is ever confirmed or remains a beautiful hypothesis, it serves as a metaphor for exploration itself. The universe doesn't owe us simplicity. It invites us to dive deeper, to question further, and to embrace the fury beneath the calm. Imagine a civilization so advanced, so hungry for energy, that they don't just build solar panels, they dismantle planets and rearrange solar systems to cage their own star. This is the audacious vision of the Dyson sphere, a megastructure theorized by physicist Freeman Dyson in 1960. His idea was simple yet staggering. An advanced society might eventually need more power than a single planet can provide, so they'd construct a vast array of orbiting collectors to harvest every photon their sun emits. The scale is almost incomprehensible. A network of mirrors, solar sails, or even a solid shell enveloping the star, converting its raw fury into usable energy on a galactic scale. But how would we ever detect such a thing? The answer lies in thermodynamics. A Dyson sphere wouldn't just absorb sunlight, it would irradiate waste heat as infrared light. Astronomers have scanned the skies for unusual infrared signatures, stars oddly dim in visible light but glowing in thermal radiation, as if something were cloaking them. One tantalizing candidate, KIC 8462852, nicknamed Tabby's star, flickers erratically, with some speculating its light could be blocked by a partially built Dyson swarm. Natural explanations like dust clouds still fit the data better, but the hunt continues with projects like Breakthrough analyzing such anomalies for signs of intelligent design. Science fiction has taken Dyson's concept and sprinted into the fantastical. Star Trek featured Dyson spheres as ancient relics of long-gone civilizations, while Ringworld imagined a single rigid band encircling a star. The video game Dyson Sphere program lets players construct one piece by piece, grappling with the mind-bending logistics of stellar engineering. These stories capture the duality of the idea, equal parts engineering blueprint and cosmic myth. A Dyson sphere isn't just a power grid, it's a declaration, a civilization's way of stamping its will onto the universe itself. The challenges to building one are as immense as the structure itself. A solid shell would be mechanically unstable, vulnerable to collisions or gravitational stresses. More plausible is a Dyson swarm, a constellation of millions of independent collectors orbiting in harmony, each adjusting its position like birds in a flock. The material requirements: dismantling entire planets, grinding Mercury or Venus into raw elements to forge the swarm's components. Energy transmission is another puzzle. Would these platforms beam power via lasers, or would they need a fleet of spacecraft ferrying batteries of antimatter? The solutions sound like magic, but they're rooted in physics we already understand. What makes the Dyson sphere so captivating isn't just its grandeur, it's what it implies about intelligence and ambition. To enclose a star is to reject the universe's indifference, to insist that life can reshape the cosmos to its needs. It's a reminder that the line between science and science fiction isn't fixed. It's a frontier waiting to be crossed. Whether these megastructures ever exist, they serve as a beacon, illuminating the farthest reaches of what might be possible when a species refuses to accept limits. And in that audacity, we find a question worth pondering. If the stars are the universe's furnaces, why shouldn't we learn to tend the fire? Consciousness might be more than just sparks in the brain. It could be woven into the fabric of reality itself. This radical idea, known as Panpsychism, suggests that awareness isn't something that emerged from complexity, but has always been here, as fundamental as gravity or electromagnetism. Think of it like this: just as atoms combine to form molecules, and molecules build cells, perhaps tiny sparks of subjective experience combine to create the rich inner lives we know as human consciousness. It's a concept that turns the universe from a cold, mechanical clockwork into something alive with potential, where even particles might possess a whisper of experience. The implications are staggering. If consciousness is a cosmic constant, then the universe isn't just a stage for life, it's a participant, a vast network of interactions where awareness flickers at every scale. Philosophers like Alfred North Whitehead argued this a century ago, proposing that reality is made of occasions of experience, not just inert matter. Modern thinkers like David Chalmers revived the debate, pointing out that neuroscience still can't explain why certain brain processes feel like anything at all. The hard problem of consciousness, as he calls it, might dissolve if experience is as basic as space and time. Science hasn't embraced panpsychism, but it hasn't dismissed it either. Quantum mechanics already blurs the line between observer and observed, with particles seeming to choose states when measured. Could this hint at a proto-conscious universe? Some theorists, like physicist Sir Roger Penrose, speculate that microtubules in brain cells might harness quantum effects to generate consciousness, a theory as controversial as it is captivating. Others, like neuroscientist Christoph Koch, suggest integrated information theory, which measures consciousness as a property of any system with the right complexity, from brains to maybe even the internet. Mystics and artists have danced around this idea for millennia. Hindu texts describe Brahman, a universal consciousness that permeates all things. Romantic poets like Wordsworth felt intimations of immortality in nature's grandeur. Even modern sci-fi from 2001, A Space Odyssey star child to a rival's linguistic aliens, plays with the notion that intelligence might be less about neurons and more about connection. These aren't proofs, of course, but they're cultural echoes of a question science is only now daring to ask. The real test, evidence. If consciousness is universal, could we detect it? Some propose looking for anomalies in quantum systems or studying whether networks like forests' mycorrhizal webs exhibit behaviors that resemble decision-making. Others suggest that if the universe is thinking, its patterns, the clustering of galaxies, the flow of energy might show traces of intentionality. It's a long shot, but so was dark matter once. What makes panpsychism so compelling isn't its answers, but its audacity. It reframes the cosmos from a silent machine to a symphony of subjectivity, where every star, every atom, might hum with some form of inner life. Whether true or not, the idea challenges our deepest assumptions, that we're separate from the universe rather than its latest way of knowing itself. And in that shift, we find not just a theory, but a mirror, one that reflects back the most haunting question of all. If the universe is aware, what does it dream? As we reach the end of our journey through the cosmos, we're left standing at the edge of something far greater than facts or figures alone can capture. The universe isn't just a collection of data points, it's a living, breathing story. One where the cold precision of mathematics dances with the warmth of human imagination. Think about the way a supernova's death throws scatter the very elements that make up your hands, your heart, your thoughts. Science tells us how this happens, but it's poetry that reminds us why it matters, that we are, quite literally, stardust given voice. Consider the humble photon traveling for billions of years across the void, only to meet your eye as you gaze at the night sky. In that moment, physics and wonder collide. The equations describe its journey, but the awe you feel, that's where the magic lives. This is the gift of the cosmic tapestry. It refuses to be confined to textbooks or telescopes. It spills over into sonnets and symphonies, into the way a child points to Orion and feels the first stirrings of curiosity. The universe doesn't just want us to solve its puzzles, it wants us to marvel at them, to let them unsettle and inspire us in equal measure. Look at how artists and scientists have mirrored each other across the centuries. Galileo's sketches of the moon's craters mirrored the chiaroscuro of Renaissance painters. The spirals of distant galaxies echo the fractal patterns in Islamic art. Even the language we use, the music of the spheres, the fabric of space-time, betrays our instinct to blend the empirical with the ethereal. The poet Muriel Rukeyser once wrote that the universe is made of stories, not atoms. She wasn't wrong. The atoms are there, yes, but it's the stories we weave around them that give them meaning. And what a story it is, a tale where black holes hide unspeakable paradoxes, where dark matter sculpts invisible architectures, where quantum particles whisper to each other across light years. Yet for all we've uncovered, the cosmos retains its mysteries like a reluctant magician, always holding one last card close. Perhaps that's the most beautiful part, not the answers we found, but the questions that still shimmer just beyond our grasp. They're the compass needles that keep us searching, keep us creating, keep us pressing our ears to the cosmic static for the next note in the symphony. So here's to the stargazers and the scribes, the physicists and the philosophers, the dreamers who dare to map the uncharted territories between fact and wonder. Whether you explore the universe through equations or elegies, through lenses or lyrics, remember, you're not just an observer, you're a participant in the greatest story ever told, one where every discovery, every poem, every moment of awe adds another thread to the tapestry. The night sky isn't just a sight to behold, it's an invitation. An invitation to keep questioning, keep imagining, and above all, to keep listening, because the universe isn't finished singing yet, and neither are